Got a big operating systems exam coming up? Think of this as your secret weapon. We're going to look at the OS not as some impossibly complex system, but as the ultimate problem solver that makes your entire digital life possible.
Feeling that pre-exam dread? Yeah, we've all been there. But don't worry, in the next few minutes, we're going to break down some of the trickiest concepts you'll face. We're talking processes, threads, virtual memory, all of it. By the end, you'll have a crystal clear study guide to help you nail this thing.
So here's our game plan. First, we'll tackle how the OS juggles a million things at once. Then, we'll dive into how it stops programs from crashing into each other. After that, we'll uncover the magic behind virtual memory, and finally, we'll wrap it all up with a quick masterclass review. You ready? Let's do it.
Okay, first up, the biggest challenge for any OS. How on earth does your computer run a web browser with 20 tabs, a music app, and your code editor all at the same time without just melting? The secret sauce involves two key ideas: processes and threads.
So think of a process as its own little private sandbox. When you double-click on an app, the OS creates a process. This gives the app its own dedicated memory and resources, completely walled off from everything else. It's how your web browser and your word processor can run side by side without messing with each other. It's all about creating order.
But here's where it gets really cool. What happens inside that sandbox? A single process can run multiple threads at the same time. You can think of threads as mini workers all helping out on the same big project. In your browser, one thread is downloading a picture, while another thread lets you scroll the page smoothly. That's why modern apps feel so snappy and responsive.
And for your exam, this slide is absolutely crucial. Here's the bottom line. Processes are heavy and independent, each in its own memory bubble. Switching between them is slow. Threads, on the other hand, are lightweight because they share memory, which means switching between them is lightning fast.
And why is this so important? Well, multi-threading is basically the engine of modern computing. It's what keeps your apps from freezing up, it makes sharing resources super efficient, it's way cheaper for the OS to manage than a bunch of processes, and it lets us take full advantage of those multi-core processors we all have now.
All right, let's move on to the next big puzzle. If threads are all sharing the same memory, what happens when two of them try to write to the same spot at the exact same time? You'd have chaos, right? Well, this is where the OS has to step in and act like a traffic cop.
This chaos has a name, a race condition. It's a total nightmare for programmers. The final value of the data depends entirely on the random chance of which thread finishes last. The results are unpredictable and can cause some of the worst, hardest to find bugs imaginable. The OS has to prevent this.
The formal name for this whole mess is the critical section problem. A critical section is just any piece of code that touches that shared data. And for any solution to be considered correct, it has to meet three strict conditions you see here: mutual exclusion, only one in at a time; progress, no one gets stuck; and bounded weight, everyone eventually gets a turn.
So how does the OS enforce these strict rules? One of its most elegant and powerful tools is something called a semaphore. The easiest way to think about it is as a simple counter, or even better, like a key to a locked room.
It all boils down to two simple operations: wait and signal. Before a thread enters that critical section, it calls wait. This is like asking for the key. If it's available, it gets the key and goes in. If not, it has to wait. When it's finished, it calls signal, which is like returning the key so the next thread in line can have its turn. Simple, but incredibly effective.
And here's the perfect analogy to lock this in for your exam. Think of the critical section as a single-person restroom. The semaphore is the key to that restroom. You have to wait for the key to become available. Once you're done, you signal that you're finished by putting the key back. It's a perfect way to ensure only one person is in there at a time.
Okay, on to the next OS magic trick, and this one is a real mind-bender. How is it possible to run a massive program, like a video game, that wants 16 gigs of memory, when your laptop only has 8 gigs of actual physical RAM? The answer is an amazing illusion called virtual memory.
Basically, virtual memory is a clever lie that the OS tells every single program. It makes each program believe it has this huge, continuous stretch of private memory all to itself. But in reality, the OS is furiously shuffling little pieces of the program between your fast RAM and your much bigger but slower storage drive.
So how does this juggling act actually work? Well, the OS breaks everything down into fixed-size chunks. It chops up the program's virtual memory into blocks called pages. And it chops up the physical RAM into blocks of the exact same size, called frames. The OS then acts like a master librarian, keeping track of which pages are currently sitting in which frames.
And that, of course, leads to the big question. What happens when the program tries to access a piece of data that's on a page that, well, isn't actually in RAM at that moment?
This triggers an event called a page fault. Now, it sounds bad, but it's a totally normal and essential part of how this all works. The CPU immediately alerts the OS. The OS then finds the page it needs on the disk, finds an empty frame in RAM, loads the page into that frame, updates its map, and then seamlessly restarts the instruction that caused the fault. The program is completely oblivious. It never even knew anything happened.
But there's a catch. What happens when RAM is already completely full? There are no free frames. Now the OS has to make a tough call. It has to choose a victim, one of the pages currently in memory, to kick out and send back to the disk to make room for the new one. And deciding which page to kick out is where page replacement algorithms come into play. This is a guaranteed topic for your exam. FIFO, or first in, first out, is the simplest. Just evict the oldest page. LRU, or least recently used, is smarter. It kicks out the page that hasn't been touched in the longest time. And optimal is the perfect, theoretical algorithm, but it's impossible in real life because it would require predicting the future.
Okay, let's bring this all home. We've just peeled back the curtain to see how the operating system is constantly solving these incredibly difficult problems, also that our computers just work. So when you think about your OS from now on, just remember this. It is the ultimate resource manager. It's an expert juggler of tasks, a vigilant guardian of data, and a brilliant magician that creates the illusion of infinite memory.
So here it is, your final cheat sheet. Burn this into your brain for the exam. Processes are independent, threads share memory. The critical section problem is all about safe sharing. Semaphores solve it with wait and signal. A page fault isn't an error. It's just a request for a page from the disk. And algorithms like FIFO and LRU are how the OS decides which page to swap out when RAM gets full.
And I'll leave you with this final thought while you study. Just think about the phone in your pocket. Right now, as you're flipping between apps, scrolling through social media, getting notifications, it is performing every single one of these complex tricks thousands of times every second. Pretty amazing, right? Good luck on your exam.